7. Wave optics. Exercises pages 184 to 185. Exercises Q1.1, page 184. Choose the correct option. Which of the following phenomenon proves that light is a transverse wave? 1. Reflection. 2. Interference. 3. Diffraction. 4. Polarization. Solution. Polarization. Exercises Q1.2, page 184. Choose the correct option. Which property of light does not change when it travels from one medium to another? 1. Velocity. 2. Wavelength. 3. Amplitude. 4. Frequency. Solution. Frequency. Explanation. Color and energy depend on frequency, and frequency does not change. The light photons are the same as the photons at the beginning. Frequency is a parameter of the source of emission of light, not the medium it is traveling through. Therefore, when light travels from one medium to another medium which is separated by a sharp boundary, the frequency does not change. Exercises Q1.3, page 184. Choose the correct option. When unpolarized light is passed through a polarizer, its intensity 1. Increases. 2. Decreases. 3. Remain unchanged. 4. Depends on the orientation of the polarize. Solution. When unpolarized light is passed through a polarizer, its intensity decreases. Exercises Q1.4, page 184. Choose the correct option. In Young's double slit experiment, the two coherent sources have different intensities. If the ratio of the maximum intensity to the minimum intensity in the interference pattern produced is 25:1, what is the ratio of the intensities of the two sources? 1. 5. 1. 2. 25. 1. 3. 3. 2. 4. 9. 4. Solution. 9. 4. Exercises Q1.5, page 184. Choose the correct option. In Young's double slit experiment, a thin uniform sheet of glass is kept in front of the two slits, parallel to the screen having the slits. The resulting interference pattern will satisfy. 1. The interference pattern will remain unchanged. 2. The fringe width will decrease. 3. The fringe width will increase. 4. The fringes will shift. Solution. The interference pattern will remain unchanged. Exercises Q2.1, page 184. Answer in brief. What are primary and secondary sources of light? Solution. 1. Primary sources of light. The sources that emit light on their own are called primary sources. This emission of light may be due to a. The high temperature of the source, e.g., the sun, the stars, objects heated to high temperature, a flame, etc. b. The effective current being passed through the source, e.g., tube light, TV, etc. c. Chemical or nuclear reactions taking place in the source, e.g., firecrackers, nuclear energy generators, etc. 2. Secondary sources of light. Some sources are not self-luminous, i.e., they do not emit light on their own, but reflect or scatter the light incident on them. Such sources of light are called secondary sources, e.g. the moon, the planets, objects such as humans, animals, plants, etc. These objects are visible due to reflected light. Many of the sources that we see around are secondary sources, and most of them are extended sources. Exercises Q2.2, page 184. Answer in brief. What is wavefront? How is it related to rays of light? What is the shape of the wavefront at a point far away from the source of light? Solution. Wavefront or wave surface. The locus of all points where waves starting simultaneously from a source reach at the same instant of time, and hence the particles at the points oscillate with the same phase, is called a wavefront or wave surface. Consider a point source of light 0 in a homogeneous isotropic medium in which the speed of light is v. The source emits light in all directions. In time t, the disturbance light energy, from the source, covers a distance vt in all directions, i.e., it reaches out to all points which are at a distance vt from the point source. The locus of these points which are in the same phase is the surface of a sphere with center 0 and radius vt. It is a spherical wavefront. In a given medium, a set of straight lines can be drawn which are perpendicular to the wavefront. According to Huygens, these straight lines are the rays of light. Thus, rays are always normal to the wavefront. In the case of a spherical wavefront, the rays are radial. If a wavefront has traveled a large distance away from the source, a small portion of this wavefront appears to be plane. This part is a plane wavefront. Exercises Q2.3, page 184. Answer in brief. Why are multiple colors observed over a thin film of oil floating on water? Explain with the help of a diagram. Solution. Interference due to a thin film. The brilliant colors of soap bubbles and thin films on the surface of water are due to the interference of light waves reflected from the upper and lower surfaces of the film. The two rays have a path difference which depends on the point on the film that is being viewed. This is shown in above figure. The incident wave gets partially reflected from upper surface as shown by ray A. The rest of the light gets refracted and travels along AB. At B it again gets partially reflected and travels along BC. At C it refracts into air and travels along CF. The parallel rays A and CF have a phase difference due to their different path lengths in different media. As can be seen from the figure, the phase difference depends on the angle of incidence θ1, i.e., the angle of incidence at the top surface which is the angle of viewing, and also on the wavelength of the light as the refractive index of the material of the thin film depends on it. The two waves propagating along A and CF interfere producing maxima and minima for different colors at different angles of viewing. One sees different colors when the film is viewed at different angles. As the reflection is from the denser boundary, there is an additional phase difference of pi radians or an additional path difference lambda. This should be taken into account for mathematical analysis. Exercises Q2.4, page 184. Answer in brief. In Young's double slit experiment, what will we observe on the screen when white light is incident on the slits but one slit is covered with a red filter and the other with a violet filter? Give reasons for your answer. Solution. In Young's double slit experiment, when white light is incident on the slits and one of the slit is covered with a red filter, the light passing through this slit will emerge as the light having red color. The other slit which is covered with a violet filter will give light having violet color as emergent light. The interference fringes will involve mixing of red and violet colors. At some points, fringes will be red if constructive interference occurs for red color and destructive interference occurs for violet color. At some points, fringes will be violet if constructive interference occurs for violet color and destructive interference occurs for red color. The central fringe will be bright with the mixing of red and violet colors. Exercises Q2.5, page 184. Answer in brief. Explain what is the optical path length. How is it different from actual path length? Solution. Consider a light wave of angular frequency w and wave vector k traveling through vacuum along the x direction. The phase of this wave is kx omega t. The speed of light in vacuum is c and that in the medium is versus. If the wave travels a distance delta x, its phase changes by delta phi equals k delta x equals omega delta x v. Similarly, if the wave is traveling in vacuum, k equals omega c and delta phi equals omega delta x c. Now, consider a wave traveling a distance delta x in the medium. The phase difference generated is
delta phi ίσον και η delta x ίσον on delta x, c ίσον omega delta x, c.
Dot opening parenthesis. 1. Where delta x equals n delta x. Dot opening parenthesis. 2. The distance n delta x is called the optical path length of the light in the medium. It is the distance the light would have traveled in the same time t in vacuum with the speed c. The optical path length in a medium is the corresponding path in a vacuum that the light travels at the same time as it takes in the given medium. Thus, a distance d traveled in a medium of refractive index n introduces a path difference equals nd, d equals dn1 over a ray traveling equal distance through vacuum. Exercises Q3 page 184. Answer in brief. Derive the laws of reflection of light using Huygens principle. Solution. Reflection of a plane wavefront of light at a plane surface. Where Mn, plane mirror, Ra and Qc, incident rays, Ap, normal to Mn, Ab, incident wavefront, I, angle of incident, Ce, reflected wavefront, R, angle of reflection. When wavefront AB is incident on the mirror, at first, point A becomes a secondary source and emits secondary waves in the same medium. If t is the time taken by the incident wavefront to travel from B to C, then BC equals Vt. During this time, the secondary wave originating at A covers the same distance, so that the secondary spherical wavelet has a radius Vt at time t. To construct the reflected wavefront, a hemisphere of radius Vt is drawn from point A. Draw a tangent EC to the secondary wavelet. The arrow A shows the direction of propagation of the reflected wave. AP is the normal to Mn at A. Angle RAP equals I equals angle of incidence and angle P equals R equals angle of reflection. In delta ABC and delta AEC, A equals BC and angle ABC equals angle AEC equals 90 degrees. Therefore delta ABC and delta AEC are congruent. Therefore angle AC equals angle BAC equals I. Dot opening parenthesis. 1. Also, as A is perpendicular to CE and AP is perpendicular to AC, angle AC equals angle P equals R. Dot opening parenthesis. 2. Therefore from EQs 1 and 2, I equals R. Thus, the angle of incidence is equal to the angle of reflection. This is the first law of reflection. Also, it can be seen from the figure that the incident ray and reflected ray lie on the opposite sides of the normal to the reflecting surface at the point of incidence and all of them lie in the same plane. This is the second law of reflection. Thus, the laws of reflection of light can be deduced by Huygens' construction of a plane wavefront. Exercises Q4 page 184. Answer in brief. Explain what is meant by polarization and derive Malus' law. Solution. According to the electromagnetic theory of light, a light wave consists of electric and magnetic fields vibrating at right angles to each other and to the direction of propagation of the wave. If the vibrations of in a light wave are in all directions perpendicular to the direction of propagation of light, the wave is said to be unpolarized. If the vibrations of the electric field in a light wave are confined to a single plane containing the direction of propagation of the wave so that its electric field is restricted along one particular direction at right angles to the direction of propagation of the wave is said to be plane polarized or linearly polarized. This phenomenon of restricting the vibrations of light, i.e., of the electric field vector in a particular direction, which is perpendicular to the direction of the propagation of the wave, is called polarization of light. Polarization of light. Consider an unpolarized light wave traveling along the x direction. Let c, v and lambda be the speed, frequency and wavelength, respectively, of the wave. The magnitude of its electric field E equals E0 sin kx omega t, where E0 equals Emax equals amplitude of the wave, omega equals 2 pi versus equals angular frequency of the wave and k equals 2 pi, lambda equals magnitude of the wave vector or propagation vector. Exercises Q5 page 184. What is Brewster's law? Derive the formula for Brewster angle. Solution. Brewster's law. The tangent of the polarizing angle is equal to the refractive index of the reflecting medium with respect to the surrounding 1 n2. Here n1 is the absolute refractive index of the surrounding and n2 is that of the reflecting medium. The angle theta b is called the Brewster angle. Exercises Q6 page 184. Describe Young's double slit interference experiment and derive conditions for occurrence of dark and bright fringes on the screen. Define fringe width and derive a formula for it. Solution. Description of Young's double slit interference experiment. 1. A plane wavefront is obtained by placing a linear source S of monochromatic light at the focus of a convex lens. It is then made to pass through an opaque screen AB having two narrow and similar slits S1 and S2. S1 and S2 are equidistant from S so that the wavefronts starting simultaneously from S and reaching S1 and S2 at the same time are in phase. A screen PQ is placed at some distance from screen AB as shown in following figure. Young's double slit experiment. 2. S1 and S2 act as secondary sources. The crests troughs of the secondary wavelets superpose and interfere constructively along straight lines joining the black dots shown in the above figure. The point where these lines meet the screen have high intensity and is bright. 3. Similarly, there are points shown with red dots where the crest of one wave coincides with the trough of the other. The corresponding points on the screen are dark due to destructive interference. These dark and bright regions are called fringes or bands and the whole pattern is called an interference pattern. Conditions for occurrence of dark and bright lunges on the screen. Consider Young's double slit experimental setup. Two narrow coherent light sources are obtained by wavefront splitting as monochromatic light of wavelength lambda emerges out of two narrow and closely spaced, parallel slits S1 and S2 of equal widths. The separation S1-S2 equals D is very small. The interference pattern is observed on a screen placed parallel to the plane of S1-S2 and at considerable distance. D from the slits U is the perpendicular bisector of a segment S1-S2. Geometry of the double slit experiment. Consider a point P on the screen at a distance y from O, y0. The two light waves from S1 and S2 reach P along paths S1P and S2P, respectively. If the path difference delta L between S1P and S2P is an integral multiple of lambda, the two waves arriving there will interfere constructively producing a bright fringe at P. On the contrary, if the path difference between S1P and S2P is a half integral multiple of lambda, there will be destructive interference and a dark fringe will be produced at P. From above figure, S2P2 equals S2S2 feet 2 plus PS2 feet 2 equals S2S2 feet 2 plus PO plus O's 2 feet 2. Exercises Q7 page 184. What are the conditions for obtaining a good interference pattern? Give reasons. Solution. The conditions necessary for obtaining well-defined and steady interference pattern. 1. The two sources of light should be coherent. The two sources must maintain their phase relation during the time required for observation. If the phases and phase differences vary with time, the positions of maxima and minima will also change with time and consequently the interference pattern will change randomly and rapidly, and a steady interference pattern would not be observed. For coherence, the two secondary sources must be derived from a single original source. 2. The light should be monochromatic. Otherwise, interference will result in complex colored bands, fringes, because the separation of successive bright bands, fringes, is different for different colors. It also may produce overlapping bands. 3. The two light sources should be of equal brightness, i.e., the waves must have the same amplitude. The interfering light waves should have the same amplitude. Then, the points where the waves meet in opposite phase will be completely dark. 0 intensity. This will increase the contrast of the interference pattern and make it more distinct. 4. The two light sources should be narrow. If the source apertures are wide in comparison with the light wavelength, each source will be equivalent to multiple narrow sources and the superimposed pattern will consist of bright and less bright fringes. That is, the interference pattern will not be well defined. 5. The interfering light waves should be in the same state of polarization. Otherwise, the points where the waves meet in opposite phase will not be completely dark and the interference pattern will not be distinct. 6. The two light sources should be closely spaced and the distance between the screen and the sources should be large. Both these conditions are desirable for appreciable fringe separation. The separation of successive bright or dark fringes is inversely proportional to the closeness of the slits and directly proportional to the screen distance. Exercises Q8, page 184. Answer in brief. What is meant by coherent sources? Solution. Coherent sources. Two sources of light are said to be coherent if the phase difference between the emitted waves remains constant. Exercises Q9, page 184. What is the diffraction of light? How does it differ from interference? What are Fraunhofer and Fresnel diffractions? Solution. The phenomenon of diffraction of light. When light passes by the edge of an obstacle or through a small opening or a narrow slit and falls on a screen, the principle of rectilinear propagation of light from geometrical optics predicts a sharp shadow. However, it is found that some of the light deviates from its rectilinear path and penetrates into the region of the geometrical shadow. This is a general characteristic of wave phenomena, which occurs whenever a portion of the wavefront is obstructed in some way. This bending of light waves at an edge into the region of the geometrical shadow is called diffraction of light. Differences between interference and diffraction. 1. The term interference is used to characterize the superposition of a few coherent waves, say, 2. But when the superposition at a point involves a large number of waves coming from different parts of the same wavefront, the effect is referred to as diffraction. 2. Double-slit interference fringes are all of equal width. In single-slit diffraction pattern, only the non-central maxima are of equal width, which is half of that of the central maximum. 3. In double-slit interference, the bright and dark fringes are equally spaced. In diffraction, only the non-central maxima lie approximately halfway between the minima. 4. In double-slit interference, bright fringes are of equal intensity. In diffraction, successive non-central maxima decrease rapidly in intensity. Diffraction can be classified into two types depending on the distances involved in the experimental setup. 1. Fraunhofer diffraction. In this class of diffraction, both the source and the screen are at infinite distances from the aperture. This is achieved by placing the source at the focus of a convex lens and the screen at the focal plane of another convex lens. Set up for Fraunhofer diffraction. 2. Fresnel diffraction. In this class of diffraction, either the source of light or the screen or both are at finite distances from the diffracting aperture. The incident wavefront is either cylindrical or spherical depending on the source. A lens is not needed to observe the diffraction pattern on the screen. Exercises Q10, page 184. Derive the conditions for bright and dark fringes produced due to diffraction by a single slit. Solution. When a parallel beam of monochromatic light of wavelength lambda illuminates a single slit of finite width A, we observe on a screen some distance from the slit, a broad pattern of alternate dark and bright fringes. The pattern consists of a central bright fringe, with successive dark and bright fringes of diminishing intensity on both sides. This is called the diffraction pattern of a single slit. Consider a single slit illuminated with a parallel beam of monochromatic light perpendicular to the plane of the slit. The diffraction pattern is obtained on a screen at a distance dA, from the slit and at the focal plane of the convex lens. Fraunhofer diffraction due to a single slit. We can imagine the single slit as being made up of a large number of Huygens sources evenly distributed over the width of the slit. Then the maxima and minima of the pattern arise from the interference of the various Huygens wavelets. Now, imagine the single slit is made up of two adjacent slits, each of width A2. Since the incident plane wavefronts are parallel to the plane of the slit, all the Huygens sources at the slit will be in phase. They will therefore also in phase at the point P0 on the screen, where P0 is equidistant from all the Huygens sources. At P0 then, we get the central maximum. For the first minimum of intensity on the screen, the path difference between the waves from the Huygens sources A and O, or 0 and B, is lambda 2, which is the condition for destructive interference. Suppose the nodal line op for the first minimum subtends an angle theta at the slit, Theta is very small. With P as the center and PA as radius, strike an arc intersecting PB at C since DA, the arc AC can be considered a straight line at right angles to PB. Then, delta ABC is a right-angled triangle similar to delta OP0P. This means that angle BAC equals theta. Therefore BC equals a sin theta. Therefore difference in path length. BC equals PB, PA equals PB, PO plus PO, PA. The other nodal lines of intensity minima can be understood in a similar way. In general, then, for the MTH minimum, M equals plus or minus 1, plus or minus 2, plus or minus 3. Between the successive minima, the intensity rises to secondary maxima when the path difference is an odd integral multiple of lambda 2. Exercises Q11, page 184. Describe Rayleigh's criterion for resolution. Explain it for a telescope and a microscope. Solution. Rayleigh's criterion for minimum resolution. Two overlapping diffraction patterns due to two-point sources are acceptably or just resolved if the center of the central peak of one diffraction pattern is as far as the first minimum of the other pattern. The sharpness of the central maximum of a diffraction pattern is measured by the angular separation between the center of the peak and the first minimum. It gives the limit of resolution. Two overlapping diffraction patterns due to two-point sources are not resolved if the angular separation between the central peaks is less than the limit of resolution in the first figure. They are said to be just separate or resolved if the angular separation between the central peaks is equal to the limit of resolution in the second figure. They are said to be well resolved if the angular separation between the central peaks is more than the limit of resolution in the third figure. Resolving power of an optical instrument. The primary aim of using an optical instrument is to see fine details, whether observing a star system through a telescope or a living cell through a microscope. After passing through an optical system, light from two adjacent parts of the object should produce sharp, distinct, separate images of those parts. The objective lens or mirror of a telescope or microscope acts like a circular aperture. The diffraction pattern of a circular aperture consists of a central bright spot, called the airy disk, and corresponds to the central maximum, and concentric dark and bright rings. Light from two close objects or parts of an object after passing through the aperture of an optical system produces overlapping diffraction patterns that tend to obscure the image. If these diffraction patterns are so broad that their central maxima overlap substantially, it is difficult to decide if the intensity distribution is produced by two separate objects or by one. The resolving power of an optical instrument, e.g., a telescope or microscope, is a measure of its ability to produce detectably separate images of objects that are dose together. Definition. The smallest linear or angular separation between two-point objects which appear just resolved when viewed through an optical instrument is called the limit of resolution of the instrument, and its reciprocal is called the resolving power of the instrument. Exercises Q12, page 184. White light consists of wavelengths from 400 nanometers to 700 nanometers. What will be the wavelength range seen when white light is passed through a glass of refractive index 1.55? Solution. Let lambda 1 and lambda 2 be the wavelengths of light in water for 400 nanometers and 700 nanometers wavelengths in a vacuum, respectively. Let lambda be the wavelength of light in vacuum. The wavelength range seen when white light is passed through the glass would be 258.06 nanometers to 451.61 run. Exercises Q13, page 184. The optical path of a ray of light of a given wavelength traveling a distance of 3 cm in flint glass having refractive index 1.6 is the same as that on traveling a distance x cm through a medium having a refractive index 1.25. Determine the value of x. Solution. Let DFG and DMM be the distances by the ray of light in the flint glass and the medium respectively. Also, let NFG and NM be the refractive indices of the flint glass and the medium respectively. Data. DFG equals 3 cm, NFG equals 1.6, NM equals 1.25. Exercises Q14, page 185. A double-slit arrangement produces interference fringes for sodium light lambda equals 589 nanometers that are 0.20 degrees apart. What is the angular fringe separation if the entire arrangement is immersed in water? N equals 1.33. Solution. Exercises Q15, page 185. Answer in brief. In a double-slit arrangement, the slits are separated by a distance equal to 100 times the wavelength of the light passing through the slits. A. What is the angular separation in radians between the central maximum and an adjacent maximum? B. What is the distance between these maxima on a screen 50.0 centimeters from the slits? Solution. Data. D equals 100 lambda, D equals 50.0 centimeters. A. The conditions for maximum in Young's experiment is given by d sin theta equals n lambda, n equals 0, 1, 2. The angle between the central maximum and its adjacent can be determined by setting m equals to 1, so d sin theta equals lambda. Exercises Q16, page 185. Unpolarized light with intensity 10 is incident on two Polaroids. The axis of the first Polaroid makes on the angle of 50 degrees with the vertical, and the axis of the second Polaroid is horizontal. What is the intensity of the light after it has passed through the second Polaroid? Solution. According to Malus' law, when the unpolarized light with intensity L0 is incident on the first polarizer, the polarizer polarizes this incident light. The intensity of light becomes I1 equals I0 halves. Exercises Q17, page 185. In a biprism experiment, the fringes are observed in the focal plane of the eyepiece at a distance of 1.2 meters from the slits. The distance between the central bright band and the 20th bright band is 0.4 centimeters. When a convex lens is placed between the biprism and the eyepiece, 90 centimeters from the eyepiece, the distance between the two virtual magnified images is found to be 0.9 centimeters. Determine the wavelength of light used. Solution. Data. D equals 1.2 meters. The distance between the central bright band and the 20th bright band is 0.4 centimeters. Exercises Q18, page 185. In Fraunhofer diffraction by a narrow slit, a screen is placed at a distance of 2 meters from the lens to obtain the diffraction pattern. If the slit width is 0.2 millimeters and the first minimum is 5 millimeters on either side of the central maximum, find the wavelength of light. Solution. Exercises Q19, page 185. The intensity of the light coming from one of the slits in Young's experiment is twice the intensity of the light coming from the other slit. What will be the approximate ratio of the intensities of the bright and dark fringes in the resulting interference pattern? Solution. Data. I1, I2 equals 2, 1. If E10 and E20 are the amplitudes of the interfering waves, the ratio of the maximum intensity to the minimum intensity in the fringe system is. Therefore, the ratio of the intensities of the bright and dark fringes in the resulting interference pattern is 34, 1. Exercises Q20, page 185. A parallel beam of green light of wavelength 546 nanometers passes through a slit of width 0.4 millimeters. The intensity pattern of the transmitted light is seen on a screen that is 40 centimeters away. What is the distance between the two first-order minima? Solution. Exercises Q21, page 185. What must be the ratio of the slit width to the wavelength of light for a single slit to have the first diffraction minimum at 45.0 degrees? Solution. Exercises Q22, page 185. Monochromatic electromagnetic radiation from a distant source passes through a slit. The diffraction pattern is observed on a screen 2.50 meters from the slit. If the width of the central maximum is 6.00 millimeters, what is the slit width if the wavelength is A 500 nanometers, visible light B 50 micrometers, infrared radiation C 0.500 nanometers, X-rays? Solution. Exercises Q23, page 185. A star is emitting light at the wavelength of 5000 A. Determine the limit of resolution of a telescope having an objective of a diameter of 200 inch. Solution. Exercises Q24, page 185. Answer in brief. The distance between two consecutive bright fringes in a biprism experiment using the light of wavelength 6000 A is 0.32 millimeters. By how much will the distance change if light of wavelength 4800 A is used? Solution. Data. Lambda 1 equals 6000 A equals 6 times 10 to 7 m. Lambda 2 equals 4800 A equals 4.8 times 10 to 7 m. W1 equals 0.32 millimeters equals 3.2 times 10 minus 4 meters. Distance between consecutive bright fringes.